All right. One of the most important topics that we are going to discuss in this first couple of weeks is the idea of vectors and vector quantities. And so for our purposes in this course, we're going to deal with two types of quantities. We're going to deal with scalars. And so scalars are any physical quantity specified with just a number and a corresponding unit. And some examples of scalars would be things I've got listed here: mass, temperature, distance, speed, or energy. And to go along with scalars, we have another type of quantity, and these are vectors. And so vectors are physical quantities that are specified not only by a number of units, but also a direction, right? And this is sort of a really critical distinction. Scalars are essentially a number of units. Vectors are a physical quantity that is a number of units and a corresponding direction. And so quantities that we're going to talk about in this course that are vectors include position, displacement, velocity, acceleration, force, momentum. And so we're going to spend this video talking about how we visualize vectors, and then how the algebra for vectors is different than the algebra for scalars or just numbers. So first off, how do we visualize vectors? Well, vectors we visualize with arrows. And so here I've got three vectors A, B, C, right, all drawn so you can see both their magnitude, which is the length, and then the direction that the arrow is pointing is the direction. So when you're looking graphically at a vector, the length of the arrow tells you the size, and we typically refer to this as magnitude when we're dealing with vectors, so the length of the arrow. And then the direction of the arrow is the direction of the vector. And so often when you're looking at these arrows, it can help to sort of connect to physical quantities. So you can think of A, B, and C here as displacement vectors or velocity vectors. The really great thing about this graphical representation is that the vector A can be any physical quantity. So could be a velocity vector, could be an acceleration vector. Graphically or geometrically, you're going to draw it the same. It's just going to represent a different physical quantity depending on the specific problem. And so let's look at this example that I've got included. A ball travels upward with a constant speed of 5 meters per second. And I note here that we can represent the velocity of the ball as a vector. And so if I was just going to draw the vector, I would just draw an arrow up. And so what we do for notation here is I'm going to use the letter V for velocity. And when we represent vectors in this course, we are going to use a little arrow over top of the letter to denote that it's a vector. Now, when we do that, immediately what we should recognize is that after the equal sign, we should have two things. We should have a magnitude, so this is the 5 meters per second that we were told about right up here, right? Speed of 5 meters per second. And then in this notation, I'm using a comma, so magnitude, comma, and then the direction. The direction in the description was that the ball was traveling upward, right? So the velocity is pointing in the upward direction, so magnitude, comma, direction. And that is one of the ways that we're going to use to designate vector quantities. Now, if we want to just talk about the magnitude, the formalism that typically gets used is this right here. So you put the vector symbol in what you can think of as absolute values signs. And so the magnitude of my velocity here is 5 meters per second. All right, now that we have introduced the idea of a vector, we want to start thinking about how vectors behave. How do we add vectors? How do we subtract vectors? Eventually, we're going to talk about how do we multiply vectors. And it turns out the way we do that is different than the numbers that you're traditionally used to working with. And so first off, we're going to start in one dimension. Right? And this is typical for how we're going to set up a lot of topics and concepts in the course. We're going to start with 1D, So the simplest case, and then we'll expand to multi-dimension. So I'm going to start with two vectors, j and k here, right? So j is a 6 meter in magnitude vector pointing to the right, so maybe this is a displacement vector. And k is a 2 meter in magnitude vector also pointing to the right. And so you can see I've drawn the two vectors here. And I want to add the two vectors together, and the way that we do this geometrically or graphically is the tip to tail method. So if I want j plus k, I start with j, and then at the tip of j, I'm going to place k, and then I'm going to connect where I started, which is over here, with where I ended up, which was over here. I'm going to draw a vector. And so that is j plus k. All right, so graphically, the tip-to-tail method is a great way to get immediate insight into the sum, or sometimes we'll call it the resulting vector, when you add two vectors together. Now, if you look down here at the algebra, j is 6 meters to the right, k is 2 meters to the right. And so when I add those two together, I get 8 meters, comma, to the right. Again, remember, we're dealing with vector quantities, and so I need a magnitude and I need a direction. And you'll notice that these two results are in complete agreement. Right, I've got an arrow here of length 8 pointing to the right, and down here I've got an 8 meter result pointing to the right. Now, related to addition, what about subtracting vectors? So again, I've still got my j and k vectors, but I want to investigate k minus j. Well, minus a vector, so here's my j vector, minus j is the same length as j, but it's pointing in the opposite direction. All right, so I've got k minus j. It turns out that k minus j is the same thing as k plus negative j. So that would be k plus negative j. Well, we already know how to add vectors. We just use the tip-to-tail method. And so here I've got k, and then at the tip of k, I place minus j, and then I connect where I started with where I ended up and make an arrow out of that, k minus j. So here is k minus j. If I look at the algebra, k is 2 meters to the right, plus minus j is 6, forgot my unit there, meter to the left. So the resulting vector k minus j, looks like I forgot my unit again, 4 meters to the left. And that is consistent with what I got graphically. Now in general, some general vector algebra rules, if you've got three vectors a, b, and c, a plus b is the same thing as b plus a. This is known as commutative or commutation. If you've got your three vectors a plus b plus c, that's the same thing as a plus b plus c, so that's called associative. And then this, the way we treat subtraction is just plus the negative vector, right? And so those are our algebra rules for adding and subtracting vectors. Now, just going to point out here that keeping track of right, left, and that minus right is equal to left, that's definitely going to get confusing. You'll notice that I used that up here. I said 2 to the right plus 6 to the left. Well, we all know this, but left, I have to know from this description that left is the opposite direction as right. And so when I add these two together, I have to know that they don't add to 8, but instead they add up to 4 to the left. And so to avoid this confusion, what we're going to use instead are unit vectors. And unit vectors are going to allow us to use plus and minus signs. So when we're doing algebra, it's going to be very clear what the resulting sum of vectors is going to be, because we're going to have plus and minus signs rather than up, down, or left, right. And so if I use unit vectors, and unit means the vectors have length 1, And we denote unit vectors with little hats. So if I say that to the right is the x hat direction, well then to the left is the minus x hat direction. And so let's look at our examples from above. J plus k. Well, j was plus 6 meters in the x hat direction. K was plus 2 meters in the x hat direction. So you add those together and you get plus 8 meters in the x hat direction, which I point out here is to the right. Now, what about our subtraction? Well, k plus 2 meters in the x hat direction minus, well, j is plus 6 meters in the x hat direction. And so this minus sign, right, is going to make this 6 meters in the negative x hat direction. So when we add those two together, we get minus 4 meters in the x hat direction, which means to the left. And so we are going to start using these unit vectors. Going to make the algebra much easier to follow and much simpler when we're setting up problems. Now, one thing that the book does is that when we're working in one dimension, unit vectors are sort of an unnecessary thing to include, because if all of your vectors are pointing along, say, the x direction, then saying plus x and minus x is plus x hat and minus x hat is a little too much information. It's a little redundant information, because if your vector's pointing to the right, that's plus, and to the left, that's minus, and the implication being a one-dimensional problem is that they're all pointing either somewhere along the x-axis, so plus to the right, minus to the left. So you'll see in the book that for 1D problems, unit vectors will get dropped because it's just assumed that all the vectors are along the x-axis. Well, okay, so we've gone over adding vectors in 1D, but what about 2D? Well, so here I've got vector A and B, and the way you add these two vectors graphically or geometrically is exactly the same way, the tip-to-tail method. And so here I've got my vector A, and then I've got my vector B, which at the tip of A, I place B, and then I connect where I started to where I finished, and that's A plus B. Now, adding vectors in 2D, incredibly easy to visualize geometrically, right? I mean, that's exactly what we just did, but it turns out it's a little difficult to quantify, particularly if you're doing it this way. And so one approach that we're going to adopt that makes it much simpler is we're going to adopt a coordinate system, and we're going to work with components of a vector. And so coordinate systems, we're going to work primarily this semester in the Cartesian coordinate system, which if you don't remember the name, you definitely will recognize the Cartesian coordinate system as sort of our typical XY coordinate system. We may see polar coordinates or cylindrical coordinates later on in the term, but primarily for most of what we work on, we're going to be using Cartesian. And so our vector A, we can represent our vector A with two perpendicular component vectors, one directed along the x-axis, one directed along the y-axis. And so our vector A, we can actually write it as the vector sum of the x component plus the y component. And you can see that that's what's going to happen here, because the tip-to-tail method, A x, A y, if you do the tip-to-tail, you end up getting vector A. So in our unit vector notation, AX gets written like this. So here's the coefficient out front of the unit vector, and instead of using x in our textbook, we use the letter I to denote the x direction. That's just a specific notation feature specific to our book. Different textbooks will use different notation. IJK for I for x, J for y, and K for z is a common set of unit vector notations, but it's equivalent to x, y, and z. And so AX, AY, and so if you want to write our vector A in our component form, you will just write AXI hat plus AYJ hat. right? So all of these, so vector A, vector A, vector A, those are all the same thing. They're just different ways to write vector A. And so when you think about component form, I've got two vectors A plus B and I want to add them together. Well, vector A is AX I hat plus AY j hat, right? So there's vector A, and vector B in general looks exactly the same, just with B's. And so if you want to add those two vectors together, the way you add vectors in component form is you group together all of the vectors along the same axis. So I add together AXI hat and BXI hat. Those go together. And the two Y components go together. Looks like I used the wrong. So this should be a J. And so I add those together. A plus B then is AX plus BX in the I hat direction, and AY plus BY in the J hat direction. So in general, if we add vectors, we break the vectors up into components and then we add up the like components together. So down here, just to talk in more general terms, our vector A can be written out as AX plus AY. And if you look at the plot over here, the figure, this angle theta can be used to denote the actual size of that coefficient, that AX value out here. So the length of A, the magnitude of A, and then multiplied for our X component by cosine of theta, and for our Y component, A sine theta. And so our magnitude for our A vector is just the Pythagorean theorem. So AX squared plus AY squared equals A squared. So that's the Pythagorean theorem. And then if we want to get the direction of the vector, well, tangent of theta right here is going to equal AY divided by AX. And that's where this comes from. And the one thing we want to be careful of is that this angle theta here, depending on where vector A is pointing, you may need to take into account the quadrant when because if you're just using the magnitude of AY and AX here, you're always going to get an angle between 0 and 90 degrees. So if your vector is pointing in this direction, you'll have to pay attention to that, or down here. Okay, and so we're ready to just talk in general. What's the format for a vector in component form? And so if you've got a three-dimensional vector, this is the general form. Again, the X component, the Y component, and the Z component. And if you're only dealing with a one-dimensional vector, let's say in the X direction, well then these two terms will just be 0. Right, so this is the most general form. If you want the magnitude of your vector, so this is the three-dimensional version of Pythagorean theorem, right? So a squared plus b squared. Typically we do this only in 2D, so that would be equal to c squared, but in 3D you have to take into account the third component. And then the direction of a vector is defined, so a hat, right? So remember that this hat is is representing the direction or the unit vector. So this would be the direction of vector A. That is the vector A divided by the magnitude or the length of that vector. All right, so you can see these two things. You just take the ratio. So in general, for vector algebra, if you multiply a scalar, any scalar, by the sum of two vectors, that scalar just distributes. So you just end up multiplying both vectors by that scalar quantity. If you have a vector A, then negative of that vector means you have to take the negative of each component. This one is incredibly important. If two vectors, if you think two vectors are equal, so if and only if these two vectors are equal, if and only if the x components, the y components, and the z components are all equal, right? So it's the only way two vectors are equal is if the components are equal for each x, y, and z. And then generalizing what we already introduced when we were adding just two vectors is that if you've got any number of vectors and you want to add them up, and again, when we add vectors, a lot of times we call the resulting sum, we call the resultant. If you want to add up your vectors, remember each vector has an I, j, and k component. You add up all of the I components together, you add up all of the j components together, and you add up all of the k components together. And so here is, let's add up all the i's, let's add up all the j's, let's add up all the k's, right? So x component, y component, z component. So when you add vectors, you simply add up the like components. And we're going to go through several examples here in class that really demonstrate how simple this approach actually makes dealing with vectors. This kind of seems complicated, but once we start looking at examples, it's going to start clicking, it's going to make a lot of sense, and it's going to make approaching these problems that leverage vectors, which is a lot of the course, it's going to make the problems much easier to work through.